Hi, and welcome back. So I'm going to start this episode by just reminding you on what I'm trying to do here with Book Club. And so the idea is that there are some really good textbooks out there that if you want to learn on your own, you can just get the book, listen to me kind of cover some of the wave tops, and really that's all the resource you need to learn this material. And I want to highlight that. So whether some of you have had, say, your undergrad in fluids, and now you're listening to this because you didn't go to graduate school, but you want to have kind of deepen your understanding, you got that book, that's great. Or maybe you did go to grad school and this is just a review. Then fine. Watching this is probably plenty for that review. Or maybe you're just trying to see, get a flavor for engineering and what does this look like. This may not be to you, this will be pretty deep. But the point here, I'm actually not trying to teach a graduate course. I'm trying to just empower you, dear reader. If you have this book and read along and with me, then you will find that you can get the knowledge. And the most important thing I ever did in my life is actually learn the ability to teach myself things. So honestly now, whatever the topic is, I can get a book or I can get review articles or all that and sort of read through and learn. And so that's what I'm trying to do here. And so especially now, because here in Panton, this kind of gets into some of the thick of it, right? This is why I've been leading the math up to this point, is because we can actually use with this math, we can get some good intuition, we can solve some real flows. But you're gonna if you're thinking I'm replacing a professor, you're gonna sit here and think, boy, Andrew's going super fast on this stuff. No, again, you're supposed to be reading it, and you might listen to me once, maybe come back and listen to it again as you sort of dig in and chew and read through this. Okay, so in chapter 11, really the kind of 11 and 12, this focuses on example flows that we can solve. Now, some of these flows, it's what people studied in academia. You need to think some of this was like pre-computers, and so what could you do? What could you understand? And so you may read through some of these examples and be like, why would we ever care about flow in a wedge or something? Well, it's less to do with we care than you could. And yet you'd have to get into like what are the point of universities, especially back in the day and things like that, to understand why is anybody going to this effort. Some of it is just basic research, and some of it is honestly it's we have to up our understanding somehow. And so, for example, in chapter 11, one of the things you can see the kind of big derivation for is like flows in a cavity, and you can get you can actually solve halfway decently for flows and kind of circling flows under a couple of assumptions. Again, this will kind of go back to kind of stream function vorticity stuff. And so you can read that one. Maybe you're just kind of going to skim over it, or if this is certainly something you're interested in. I actually did some research work in really Bernard convection, so this kind of piques my interest. Would be super interesting, but it's a very detailed solution that I'm not going to get in here. It is pretty math heavy, but you can see with all the tools we've built and sort of been built up, especially in Panton's book, that you can show how you can solve those things. Okay. Another interesting one is the oscillating Stokes layer. So this is a fluid and a boundary, and you're basically oscillating that boundary back and forth, and you kind of get into what's the sort of fluid oscillations and how does it kind of radiate away. Okay, so also super interesting. How many times do you have an oscillating fluid? There are certain instances you can think through, but again, this is like it can be solved, but it actually gets you to start understanding sort of diffusion of information and diffusion of viscosity starts getting into your head. So this one's not as bad. Okay, and then one of the ones I am going to work through a little bit. One is a vortex, okay, that's decaying. Okay. This is important because we'll actually, as I get into kind of vorticity equations, things like that, we'll want to have an idea of decay. Right? So if you say that there's a theta velocity, right, going around, and it is some constant circulation number over 2 pi r. So it's not a function, just a number. Pick a number that would be like, you would imagine that as the vortex strength, and that this is the solution. Okay. And so when you go through, and you would have to use the kind of the polar coordinates version of a momentum equation. When you do that, you'll have that the time rate of change of v theta with respect to time is equal to minus, this is kinematic viscosity, over r squared, the derivative of R v theta respect to R plus kinematic viscosity 1 over R, second derivative of R v theta respect to R squared. Okay. And then the solution to this is, again, one of these similarity solutions. A very powerful mathematical tool that you actually see again and again and again in graduate fluids here. So I'm going to define gamma. Again, unfortunately for us engineers, we reuse terms all the time, so this is not ratios. But this is gamma to be consistent with Panton in the book. And this is R v theta and over R over 2 pi. Okay. So when you go back through and you use a similarity variable, I'll just write down similarity variable, R over square root nu t. And then you plug this back up into the equation. You're then going to get the final differential equation of the form f double prime plus eta over 2 minus 1 over r f prime equals 0. Okay, and this has a very specific solution. Okay, it's basically 1 minus exponential minus eta squared over 4. And so what does this look like? This looks like a system here that should be theta, sort of a decaying system like this. So that this is sort of as time increases. Okay? Time. Yeah. So it's a decaying vortex. So you see the strength showing up here. Okay? So this means that we'll come back to this. If you have motion in a circle, like swirling velocity, you always will have some viscosity. If it's a high Reynolds number system, yes, that viscosity is not very strong compared to the inertia. But eventually you will have an eddy, the size that viscosity is important, and that viscosity is going to just basically take that eddy and decay that eddy, decay that vortex away. Okay, this is actually a key part. We touched on it in that sort of turbulence appreciation, and now finally here, through a very kind of simplistic system, we can actually, no kidding, have an analytical form that proves sort of this decay of vorticity. Okay, and so it's an important step, right? So there's all sorts of like vortex breakdown and all sorts of cool things that this does. And I'll put up here one more flow that can be solved for quite a bit, and that's actually stagnation. Okay, and so that stagnation flow, is effectively you can imagine it as a surface, but it's a linear. Effectively, the velocity, if I call a new variable, sort of distance from, let's call that y, then you see it ends up being like a linear decay. Okay, so these are all important things, and again, like I'm an engineer that builds real things. So to me, this is like stagnation flow into an airfoil, even though the theory is sort of built up a stagnating flow into a wall. I know you can't stagnate straight into a wall. So this is like, we know analytically that the velocity that goes from sort of infinity and then down linearly down to 0 right there at the wall. And then the solution you'll see in Panton is actually they'll explore what happens sort of off the wall. And there are all of these mathematical expansion terms that can kind of help you understand what's going away, just away from the wall. So, and this is super important, especially, like say, hypersonic flows, and this is stagnation. So it's hot, and then the flow next to it is still partially hot, but now it's starting to speed up, and I get heat transfer rates. Okay, this is super important, like I mentioned, for sort of turbulent decay and things like that. So, all of these kind of chapter 11, chapter 12. Like I said, I don't want to convey it's optional reading, but the depth that you go into it is sort of choose your own adventure there. What's important, like, if you were taking this in graduate class, you would absolutely kind of have to crank through some of these. So I recommend, following along a road, recommend doing some of those problems. Just you have, you end up having some of the tool sets. Like I sort of blast through the similarity solution and the final differential equation. But, go do it. Go walk through this. You have plenty of math to go do it, okay? And then I'm actually going to, right here, I'm going to make myself enough space. There's a problem set in Panton that I'm actually going to do. And I didn't put down what number it is. But you'll see it in the back of the book. But because when we get to chapter 13, where I'm really going with this entire lecture, is we're going to finish with vorticity and the vorticity equations, and then what we can actually say just about the equations. And I'll sort of finish with why we build wind tunnels the way we do. Okay. And so to get there, a couple steps. The first one is we have to prove, the question is basically prove that, this term that we see, this sort of convective derivative, the jth velocity times jth derivative of ith velocity, that's the advection term, it's buried in the material derivative. It's saying prove that this is the same as the gradient of kinetic energy. So that's 1/2 uj, right, velocity squared, 1/2 velocity squared, minus the curl, so that curl is epsilon ijk, the cross of velocity with vorticity. So that's the jth velocity with the kth vorticity. Now, remember, we have already defined vorticity, KLM of the nth derivative of the nth velocity. So we're going to use that here in a second. Okay, basically it's the curl of velocity is vorticity, and this represents velocity crossed with vorticity using our Einstein notation. Okay, I'm going to switch to green. So this shows up a little bit better. Okay, so the first thing we're going to do here, those are two j's. So there are two terms, and so this taking the derivative, it's twice. So it gives rid of the 1/2. Okay, so the first thing that happens is that this is simply equal to uj del I of uj. That's just expanding that straight up. Okay, now let's come in here. So let's write that. So that is epsilon ijk, and then I'll go ahead and input the definition above, and you can always move the Vicevita tensor over. So KLM, the nth derivative, and then write this all right. So actually, not quite nth derivative. So sticking order is important. That's uj, and then nth derivative of the nth velocity. Okay, so that's just a direct substitution there. Okay, now a little blackboard magic for you, but the property of this Levi-Civita tensor, that the order, if you swap any two of these, you pick up a negative sign, or if you just keep the order the same, you don't swap a negative sign. So this is the exact same as saying a Kij, a KLM, right? So it's the same thing. And then there's actually this property, and I know I haven't covered it here in the lectures. Hopefully, if you were doing your reading, you saw this in chapter 3 when Panton was going through this. There's actually, this has a fairly simple deconstruction, which is, again, why Einstein notation is nice. So this is the same, and I'll just write it del del minus del del. It's the insides, so the inside is IL, JM, inside, or sorry, left, right, minus outside, inside. And so the outside is IM, and the inside is JL. Okay, so that's the same thing. So when I flesh that out, write this again, UJ del I UJ minus. Now let's do this. So I'm going to be careful. I want to keep I's and J's. That's going to be my choice. So when I see this del's, Kronecker deltas, that means I can just swap those indices. But I feel like you're summing over, again, not that I'm cheating here, each repeated indice, so J and K and L and M are all summed. The only thing that actually survives this is the I. So this is still a vector. The answer to this mumbo jumbo is a vector. Okay, so let's do it out. And so that means L is going to go to I, so that there's my J. Del L, this one means it's now del I. And then J is actually UM, so del I of UJ. Well, that's interesting, right? You see that one on the left? And then minus of minus, so that's then a plus, and this IM, so that is a UJ, and L becomes a J, so that's del J, and then I becomes an M. or n becomes an I if u I. Well, there, we literally finished with it. Maybe switch back to orange so you can see it, because those two cancel, and so this is literally uj del j of ui. Okay, so it actually is the convective, sort of convective form, so I've proved it. All right, why is this important? Because when we actually derive the vorticity equation, it's actually easier to start here. And so that's what I'm now going to kind of do on this this side of the board. All right, so writing the full momentum equation, I'll start here. So del I del T plus, again, the gradient of convection, or sorry, kinetic energy, minus, minus I j k. Oh, that's why it's plus. We're swapping those two terms. Sorry, so this is a w j u k. Just like I talked about, when if you swap the two indices, negative goes to positive. So that's the only difference between this. On this, I'm going to swap j and k, so that I can put this on the other side. All right, so that's why I pick up a plus, and that's equal to the negative of the pressure gradient. And this is all non-dimensional. I was wondering where my densities went to. 1 over derivative, and I'll just do nabla squared ui. All right, so still, okay, all right, still on the board. I'm getting close. Okay, so we're now going to take effectively the curl of this equation, right? And so what we're going to do is E P Q I, and then I'm going to take the qth derivative of that entire thing. Okay, so that's where we're headed. All right. So the time derivative, it commutes with the spatial derivative, so I can kind of cross them back and forth. It doesn't matter. And so that term is then literally just the pth derivative, or the pth vorticity with respect to time. All right, so that was easy. And then, so here, write that down, P, Q, I, and then there's a del Q, and then there's a del I of this stuff. I'm going to jump there, but basically I'm going to stop. These two, so Q and I, this is the whole point here, is that this is symmetric on Q and I, and this is anti-symmetric on Q and I, and so the multiplication of that is 0. All right, so that entire term wipes out because of that property. That's actually why it was easier to start with this, because it just blasts that away. Okay. Okay. Then we have, again, E, P, Q, I, epsilon I, J, K. There's a del Q of, again in parentheses, because it's of the whole term, omega J, UK. Now, what happens to this? It's actually the same sort of thing, so I'm not even going to write it. So there's a del Q and a del I, and then this is same thing. It's anti-symmetric times symmetric, so that term is going to go away. And then this thing, the nabla, is linear. Well, it's just del J, and so that's going to pass through. And so this is literally just then 1 over Reynolds nabla squared of omega P. Okay. Now, same sort of trick. We're going to do this outside, left, right, outside, inside thing. Okay. And so I'm going to rewrite this easily. This is the same thing as I'm bringing I to the front. I PQ, I JK. And so then this is then equal to, again, a del minus del. All right, so left, right, so that's PJ, QK, minus outside in, that's PK, minus del of QJ. All right, so we have d omega P, respect to time. All right. And so that is then, let's go back up here. So Q is going to go to K. So that first thing I get is a del K. And then I'm saving P, right? Because P is actually my vector. So J is going to P. So it's del K of omega P. And then that is a UK. All right. And then a minus. And then here is P goes to K and J goes to Q. So that's del Q of J goes to Q, so omega Q, and then K goes to P, so UP. Right, equals 1 over Reynolds del squared omega P. All right. So let's expand out those two terms. So you get a omega P del K UK. Orange is failing on me. Omega P del K UK, and you get a UK del K UP, omega P. All right, sorry, that was getting a little messy. But basically this is all for incompressible, so that goes to 0. All right, and then you get a UP del Q of omega Q, and you get a minus omega Q del Q UP. All right. The divergence of velocity is of this is 0, right? This is the gradient of the curl of a so that's also 0, and then 1 over Reynolds del squared omega P. All right. I'm going to have to switch to a completely different color because those are getting blasted. Let's see, can you see that at all? Yeah, all right, you can see that. Out comes the yellow. All right, so we're basically done. And so this is now that, by the way, I'm left with P's and K's. That's not normally how we write it. So I'm going to do one last little blackboard magic, which is now at this point, I'm going to let P go to I, and I'm going to let K go to J, because it doesn't matter, right? Every time there's K's, it's actually a sum. Okay, there was a sum there. Okay, in fact, there was a sum here, so it doesn't even matter how I do it. Yeah, so what's now left is, so again, P going back to I, this is the ith vorticity. I'm going to change to I. This was left, so I'll write that as a uj del j, and then omega I. So boy, that sure looks like the material derivative of vorticity. And then that's equal to, I'm going to push this term to the other side, that's equal to omega j del j of ui plus 1 over Reynolds del squared omega I. All right, we're done. So that is the vorticity equation. Now, one of the reasons we do this is because how powerful this is then to sort of analyzing. Any real flow is going to have these decays, especially when you're talking about turbulence. And so what this looks like is the transport of vorticity has a source term. So this is some sort of source, right? It's the thing that's going to add to it. And then this is effectively the where it disappears. Okay, like that. Again, curvature is normally the del squared, and you end up getting negative, so it diffuses, right? This is a diffusion, so it kind of spreads it and drains it from an energy point of view. Okay, so the first thing that happens is, I'll draw it maybe here, kind of back up to the real flows. One of the things, and we'll actually come back and talk about it later, but as an airfoil sitting here, not moving, think of an aircraft on a runway. It's not moving yet. And then it starts moving. Let's see if my blue will come up. No, blue's not going to work. All right, maybe back to orange so you can see it. Because effectively it's all conserved, then what ends up happening is you get, because you get circulation around the front, you get circulation around the back. And so you get what they call a starting vortex, and you can actually prove it here. So that's pretty cool. We actually saw this in Goochman as well when I was doing that book club. So that one's neat, okay? The second thing is actually on sort of turbulent wall-bounded flows. If here's the wall, and this is you're sort of in a boundary layer, right? So the average is doing that, but you have all of this crazy twisting and tumbling and vortices. So I want to take you a look at, think of a term here. So what would be the y vorticity? So that would be a vorticity sort of in the y direction. So again, a vortex that sort of almost looks like it's sitting on the wall here, or sort of sitting in the plane, and then times the derivative of the y derivative of u. Well, we know for sure it's sitting in a gradient, right? Look at that. And so it's actually saying that's going to increase the x vorticity, right? Because this was the x velocity. And so any sort of in-plane vortex like that meets that gradient, is going to increase it. So what that actually ends up doing is that as this thing goes up, it sort of bends over the vortex, okay? And so that's where you get these beautiful sort of horseshoe vortices, and that bends over the vortex, which then creates, vortex, which then creates a suction layer. So you actually can look at this and start seeing, if you get into turbulence and flows visualization, you'll see how this sort of turbulence sort of keeps self-generating through some of the stuff, and it actually pops out from this equation. Okay. The last piece is if I have a vortex. So imagine like a tube, and then I sort of pull on it. So that if this tube is going and I get it tighter, I pull on it. It's going to effectively intensify it. But then after I've intensified it, the nobular term is going to come in here and decay it. So basically, if I take a vortex and I pull it in one direction, okay, so that would be a vortex in the x direction. I pull it, it's going to intensify it. So by pulling it again, think about this would be a wx times the gradient of u in x direction. It's the same thing here. Same different term. I picked on sort of the middle term of when j was equal to y, but this is basically pulling on it by saying there's a gradient in the x direction. I'm going to pull on it. Okay, this is sort of the punchline for this episode. When you have a wind tunnel, and I'll draw it right here, okay? When you have a wind tunnel, there's two things you do on this front screen of a wind tunnel. So next time you're in a lab or you go look at some videos, there's two things you do to make this wind tunnel work. Okay, the first thing is sort of right in front, you have this grid. And it's a really tight grid. And so what is that grid doing? What's actually doing is cutting all of the in-plane vorticities that are large and sort of trapping them, cutting them down to only small scales, okay? Sort of as you're sort of sucking it in, one is sort of generally, you're creating that acceleration, but you're sort of going from real gentle flows. This is back to sort of entrance vortices and things like that, okay? But then this constriction is creating this du dx, which was this term. And so then any remaining small vortex here in the x direction is actually going to be intensified and shrunk to where diffusion comes in and cleans it up. And so then that's why right here you'll then have your actual test section. So what you've done is any kind of fluctuation in turbulence, what you've done is you blocked it off, you tugged on the ones in this direction. The ones that are out of this direction actually couldn't even occur because this grid is usually got some length. So any kind of sideways twisting is now sort of stopped. This also helps, any boundary layer helps suck down the boundary layer. We've shown that before. And then this remaining piece takes any remaining vortex and twists on it and diffuses it. So it's how you actually create, as much as possible, a pristine, then sort of temporarily you've made this a pristine slug of air to go into your wind tunnel. And, where you've got a car model or an aircraft model. Because when an aircraft's flying through the atmosphere, the air is usually sitting there. Let's not talk about weather and when we call turbulence in front of an aircraft. Just usually the air is sitting there and the aircraft is flying through it. And so it's usually quiescent, undisturbed air. So to get that quiescence, this is why wind tunnels are shaped like this. And it's due to, you could see it here in the vorticity equation, due to the sources, what happens with the sources, and then you sort of tug on it, you intensify it, you actually create more curvature, and the diffusion kills it. So, anyways, that's a powerful portion. I wanted to walk through this just because this can be one of the pieces that you get totally lost in the muck. You should be able to follow sort of the cavity flows and the oscillating flows and some of the stagnation flows. Here you can get absolutely stuck in the muck. I wanted to walk you through it because in the end, the application is it's so important. And really, it's just like how when we did the math to get into Einstein notation because it was powerful, this is almost, when you get into the world of real aircraft or real cars or real turbulence, honestly, like framing your fluid mechanics conservation momentum as sort of this is often more powerful than framing it in terms of this. And all we did was just take the curl of it. Okay, this is often many times the better way to think about fluid mechanics. So, man, good episode. Hope you stuck with it. Again, the point of book club is that you're reading and doing this stuff. This is not intended to replace that knowledge that you would get from reading or the knowledge that you're getting if you're actually in graduate school and you've got a professor that is lecturing on this stuff sort of day in, day out and kind of walking you through. So go be empowered reader. This is how you learn by yourself, and hopefully I'm helping you out here. So we'll see you next time.